Now, next question is that the simple pendulum. Define the simple pendulum and obtain the expression of periodic time of a simple pendulum. Already we discussed about that the oscillation of a pendulum is represent the simple harmonic motion. So what is the periodic time of the oscillation of simple pendulum? We are interested to derive this equation. For that purpose, first what is the definition of simple pendulum? For that purpose here, a small massive body suspended by a light, inextensible and twistless string from the rigid support is known as the simple pendulum. The system of a small massive body suspended by a light, inextensible and twistless string from a rigid support is known as simple pendulum. Again, what is the definition of simple pendulum? The system of a small massive body suspended by a light, inextensible and twistless string from a rigid support is known as simple pendulum. Here we do the figure of the simple pendulum. That is the rigid support. Here the string, light string, inextensible, and at the free end of a string, here the body is suspended, body of mass M. There is an equilibrium position. This system is known as the simple pendulum. As we slightly displace this body from its equilibrium position and release, so it performs the simple harmonic motion about its mean position. Now, here we mention the position of the pendulum at point A. At point A. So the path of its oscillation is this. Angle made by the string with the vertical direction is theta. The tension act on a body towards the point of suspension, that is the ODS, that is the O point. Now the distance between point of suspension to the center of mass of a body, that is known as length of a pendulum. That is known as length of a pendulum. That is known as a length of a pendulum. Clear? Okay. Now the definition of length of a pendulum. The distance between point of suspension and center of mass of a body is known as length of a pendulum the mass of a simple pendulum is concentrated at the center of gravity of a suspended body. The mass of a pendulum is concentrated at center of gravity of a suspended body. So now the definition of simple pendulum, the system of a small massive body. Here the body is very small. This having the mass is suspended by a light string. Light inextensible, that means the length of a string is not increased, and twistless string from a rigid support. Such system is known as the simple pendulum. The distance between the point of suspension or the rigid support and the center of mass of the body, that is known as the length of a pendulum L. The entire mass of a simple pendulum, that means the mass, whole mass of a pendulum is concentrated at center of gravity of a suspended body. Now, as shown in the figure, we are going to derive the equation of periodic time. For that purpose, as shown in figure, consider a simple pendulum. As shown in figure, consider a simple pendulum a small body of mass m, the small bob of mass m is tied with one end of massless and inextensible string, while other end of a string tied with a rigid support. What is shown in the figure? That is the simple pendulum. In simple pendulum, a small bob of mass m is tied with a one end of massless and inextensible string, while the other end of a string is tied with a rigid support. Now, pendulum is oscillate in vertical plane. Now, a simple pendulum is oscillate in a vertical plane. Suppose the theta be the angle made by the string with the vertical. Let theta be an angle made by a string with vertical. So there are two forces acting on a body. One is weight force mg is in downward direction. weight force acting in downward direction mg. Now there is the direction of strain. Here the angle subtended is theta. So this component is mg cos theta. There is the parallel component, and another component is there is mg sin theta. mg sin. Now the forces act on a bob of a pendulum at point A are first tension in a string towards a Z support, and second weight mg of a body in downward direction. In downward direction. So first the description of the figure. As shown in the figure, consider a simple pendulum. A small bob of mass m is suspended by massless and inextensible string, while the other end of a string is tied with a Z support. Okay. Now a simple pendulum is oscillate in a vertical plane. This plane, it is free to oscillate. Now theta be the angle made by the string with the vertical direction. Therefore, the forces act on a body at position A, at point A. First is the tension acting or the tension in a string towards the point of suspension. And second is the weight mg of the body is in downward direction. Now here we have to consider the two components of weight mg. One is the parallel component mg cos theta. That is known as the radial component of mg, right? And second is the perpendicular component mg sin theta. That is perpendicular to the length of a pendulum. That is known as the tangential component of weight mg. Out of these two components of weight, which component is responsible to produce the torque? Clear? Okay, we discuss this thing. Now consider the component of weight mg. Of weight mg. First is parallel component. mg cos theta. Along the string, it is radial component of mg. The total radial force is T minus mg cos theta, and radial acceleration is omega square L, and radial acceleration is omega square, but torque due to such component due to radial force is 0, because the line of force passing through the rigid support that means we prove that the mg cos theta component of weight mg is not responsible to produce the torque. Again, we consider the component of mg, two components of mg. One is first the parallel component mg cos theta along the string. It is known as the radial component of mg. The total radial force is T minus mg cos theta. Here we consider this component of force, that is the mg cos theta. That is along the direction of string. Therefore, the resultant force is T minus mg cos theta. Right? Now, and radial acceleration is omega square m. But the torque due to the radial force is 0. Because tau is equal to R cross F. R cross F is equal to Rf sin theta. Theta is the angle between the R and F. Here I is our L and F is equal to our T minus mg cos theta into sin theta is equal to pi. Sin pi 0. Therefore the torque is also 0. Torque is also 0. Because already we learned about this in rotational motion. If the line of action of force passing to the point of suspension or our reference point, the torque produces 0 in spite of the I and F are non-zero. And second component is perpendicular component. mg sin theta is known as tangential component. Tangential component of mg. Therefore, the tangential force is mg sin theta. The torque due to tangential force is from tau is equal to Rf sin theta. Tau is equal to Rf sin theta. Here tau is equal to minus L mg sin theta. That is the equation number 1. Here negative sign indicates such torque is destroying torque. Tends to reduce the angular displacement and therefore the negative sign is placed in this equation. Here, due to this empty sign theta component, the theta, that means the angular displacement of a simple pendulum is reduced. Because as it can more and more distance, so mg is going to increase, theta is increases. Therefore, mg sin theta is acting towards the point of suspension. Right? Therefore, that is the requires toward is it. Now, for rotational motion, Newton's second law is tau is equal to I alpha. Now, what is the rotational motion? Here, the 1/4 part of whole rotational motion is take place due to the mg sin theta component. Here, the simple pendulum will oscillate between these 2 points. Actually, there is some part of the rotational motion. For rotational motion, the torque is important. That means, whatever the importance of the force for linear motion, the same importance of the torque for rotational motion. And due to that result, here we obtain the equation of the torque. Now, in linear motion, the Newton's second law of motion is F is equal to ma. Right? Now, for rotational motion, the same equation, the force is 10 for the torque. And instead of the mass, here the moment of inertia is used. There is the linear acceleration, here the angular acceleration alpha. So tau is equal to I alpha. There is equation number 2. Here I is moment of inertia of a body about with respect to rigid support. With respect to rigid support. And alpha is angular acceleration. Now comparing equation 1 and 2. Comparing equation 1 and 2. What do you think? I alpha is equal to this minus mgl sin theta. I alpha is equal to minus mgl sin theta. If the theta is very small, therefore sin theta is approximate theta. Therefore I alpha is equal to minus mgl theta. Minus mgl theta. Therefore alpha is equal to minus mgl upon I into theta. Now alpha is equal to d omega by dt, and angular acceleration. Now angular acceleration alpha is equal to d omega by dt. What is the omega? Omega is the angular velocity. That is similar to this equation. A is equal to dv by dt, and v is equal to dx by dt. And angular velocity is omega is equal to d theta by dt. Theta is equal to angular displacement. Yeah? Okay. Therefore, alpha is equal to d square theta upon dt square. Substitute in equation 3. Therefore, d square theta upon dt square is equal to minus mgl upon Therefore, equation 3 becomes, instead of the alpha, we substitute this value, d square theta upon dt square is equal to minus mgl upon I into theta. That is the equation number 4. That is the differential equation for rotational motion. Clear this? Okay. Now listen again from this side. Here we consider the two components of weight mg. First is the parallel component mg cos theta along the direction of string according to our dx figure. The direction of string is this, so mg cos theta is our radial component. Okay. Therefore, the total radial force T is towards the point of suspension, mg cos theta is in opposite direction. Therefore, the total force is, there is the T minus mg cos theta. T minus mg cos theta. And radial acceleration is omega square. But torque due to the radial force is 0. Because the line of radial force passing through, line of this radial force is passing to the point of suspension. Therefore, the torque becomes 0. Now, second component is the perpendicular component mg sin theta. That is known as the tangential component of mg. The tangential force is mg sin theta. The torque due to the tangential force is tau is equal to r, from equation tau is equal to r sin theta. Here instead of the distance r, here the length of the pendulum n. F sin theta, F is equal to, here force is mg sin theta. Therefore, here the negative sign indicates the torque is restoring torque and tends to reduce the angular displacement of the pendulum. Now, for rotational motion, Newton's second law is tau is equal to I alpha. Here, I is the moment of inertia of the body with respect to the z support, and alpha is the angular acceleration. Comparing equation 1 and 2, so we obtain I alpha is equal to minus mg sin theta. If the angular displacement theta is very small, so we can add the sin theta is approximately theta. Therefore, I alpha is equal to minus mg L theta. Therefore, alpha is equal to minus mg upon I into L theta. Now, what is the alpha? Alpha is similar to the acceleration. Linear acceleration is A. At that time, the dv by dt, and v is equal to dx by dt. The same way for rotational motion, alpha is the angular acceleration, d omega by dt, but omega is equal to d theta by dt. Therefore, d square theta upon dt square. Therefore, equation 3 becomes d square theta upon dt square is equal to minus mgl upon I into theta. This is the differential equation for rotational motion. Okay, last we did this equation, d square theta upon dt square is equal to minus mgl upon I into theta. Is the similar equation of differential equation for of simple harmonic motion. Is similar to the differential equation of simple harmonic motion. That means that d square x upon dt square is equal to minus omega square x. That is the differential equation for simple harmonic motion in terms of x, that is in terms of theta. Here double derivative of angular displacement, here double derivative of linear displacement x. Here variable is x, here variable is theta. Therefore, this part is same as the omega square, minus omega square. So comparing equation 4 and 5. So what you obtain? Omega square is equal to mgn upon I. Therefore, omega is equal to square root of mgn upon I. But omega is equal to 2 pi upon t. We are interested to obtain the equation of the periodic time of simple pendulum. Here this equation is similar to the differential equation of simple harmonic motion. Thus, the motion of a simple pendulum is simple harmonic motion. Here we had one verse. Thus the motion, thus simple pendulum perform a simple harmonic motion. Simple harmonic motion. Now comparing equation 4 and 5. 4 and 5. What's happened? Omega square is equal to mgn upon I. Therefore, taking the square root, omega is equal to square root of mgl upon I. But omega is equal to 2 pi upon t. Substitute here. 2 pi upon t is equal to under root of mgl upon I. Therefore, periodic time t is equal to 2 pi upon under root of mgl upon I. Therefore, periodic time of simple pendulum is t is equal to 2 pi under root of I upon mgl. That is the equation number 6. But here I is the moment of inertia of a pendulum with respect to its support. But I is equal to ml square is equal to moment of inertia of a simple pendulum with respect to its support. Therefore, T is equal to 2 pi under root of ml square upon mgl. 1 times mm cancel, 1 times L cancel. Therefore, 2 pi under root of L upon C is the equation of periodic time of a simple pendulum. From equation 7, thus P is directly proportional to the under root of L and inversely proportional to the 1 upon under root of G. So that is the equation of periodic time of a simple pendulum. Again, my last equation is that we obtain the differential equation for rotational motion by using the substitute the value of alpha. This square theta upon dt square is equal to minus mgl upon I d theta. Is the similar to the differential equation of simple harmonic motion. Differential equation of simple harmonic motion is this: d square x upon dt square is equal to minus omega square x. Now comparing equation for n, so what's happened? So omega square is equal to mgl upon r. Here both equations are similar, therefore simple pendulum performs the simple harmonic motion. Okay. Taking the square root on both sides, omega is equal to under root of mgl upon r, but omega is equal to 2 pi upon t, substitute here. Therefore t is equal to 2 pi under root of mgl upon r. Therefore periodic time of simple pendulum is t is equal to 2 pi under root of I upon mgl. But we know that moment of inertia of a simple pendulum with respect to its support is ml square. We learn about this equation in rotational motion to find out the moment of inertia of different shape of a body with respect to the different axis. Therefore, we substitute I as ml square. Therefore, m and 1 times l cancel. Therefore, t is equal to 2 pi under root of l upon g. Now, simple pendulum is also in your syllabus of practical to find out the periodic time, and on the basis of this, we have to find out the gravitational acceleration of the Earth. So, from this equation, making the square, g is equal to 4 pi square l upon t square. Clear?